Hi, welcome to Dr. Pat TV. Today we're looking at U-substitution. I gotta be upfront here. I'm gonna be doing this probably in a different way than you've seen in other classes or what other classes will do. I will get to what the formal U-substitution, the way people do it across the country, but I just kind of want to have some fun here and maybe get a little bit of idea of what's happening with this thing. All right. And so what I'm playing with here is the chain rule. So U substitution is actually the opposite. It's the reverse direction of the chain rule. We did the chain rule for derivatives. If you remember our steps for the chain rule, we took the derivative of the outside piece and then we multiplied by the derivative of the inside. It was kind of like eating that orange. You do the outside, peel that orange, leaving the inside alone, and then off to the side, you multiply by doing the derivative of the inside. You break those wedges up. Okay, and so, Jay, if you're not remembering that, let's just do an example real quick. So we've got this function here. We want to take its derivative. I've got an inside piece here, the parentheses, the inside piece, and then I got a power 8. So hopefully you remember we do the outside. So we deal with the power 8 using the power rule by multiplying the 8 and then subtracting 1 from the power. But we left the inside alone, and then times the derivative of the inside. So we take the derivative of x to the 6th. And that's where we're seeing a 6x to the 5th. And then plus 2x to the 3rd. That's why you see this 6x squared, because that's its derivative. Okay, and so then if you want to clean that up, you can factor out a 6 if you wanted to. But the catch here is when we're doing the derivative and the chain rule, we're leaving the inside alone, doing the derivative of the outside. That was our first step, do the derivative of the outside. And our second step was do the derivative of the inside. Sometimes your numbers are factored out, so there's a 48 there. I took the 6 out there. So just wanted to be aware of that. Numbers get kind of moved around. Okay, and so that's the chain rule. So if we want to do the inverse chain rule, then we're taking those two steps for the chain rule and we're doing the opposite thing in the opposite order. We're going to divide the derivative of the inside. That's what we're going to do first. We're going to divide the derivative of the inside, and then we're going to take the antiderivative of the outside piece. Okay, so we're just doing the opposite things in the opposite orders. That's what the antiderivative does. That's what inverses do. So that's that whole inverse relationship. Now, there are a whole bunch of technicalities, so I'm just going to do some nice, brief, easy examples, and then we'll do the actual full-blown U substitution, so that way it'll take care of all our things for us. All right, so let's, before we get there, I got to make sure that we all understand that this little step here only works if we're doing the reverse of the chain rule. So we got to be able to identify who's good for the club, who can get in, who can't. So what I'm going to do is I'm going to give you two functions, a pair of functions, and then we're going to identify which one was the result of the chain rule. So there's two fractions. Which of those two is the result of the chain rule? And so what we're doing is we're kind of looking at that. I'm going, hey, if I make the inside part being inside the denominator, the derivative of that piece would be 2x, because the derivative of 1 is 0, so that goes away. So we've got x squared plus 1, its derivative is 2x. Hey, there I see a nice 2x. Whereas on the second fraction, it just has a 2. It's missing that x. It's missing the component of the derivative. And so basically, that one would be the result of a chain rule. So we took the derivative of something and got this one. This piece right here was the result of a chain rule, its derivative. Now, of these two, which one is the result of a derivative of the chain rule? Well, again, we're looking at who's inside and then do we have its derivative? That's the key. Before I can do the antiderivative steps, the two steps to go backwards, I got to make sure that I have a piece that is the result of the chain rule. If I got a derivative that's not from the chain rule, I can't be using the opposite steps of the chain rule. It's something completely different. All right, so then I'm looking at who's inside, who's outside, and one of the tips is look for the roots. The roots are usually the stuff inside is the inside piece, not the parentheses around here. It's the inside piece here. And so I'm looking at the inside. I'm seeing x to the 5th minus x. And when I take the derivative of that, I get 5x to the 4th minus 1. I'm looking around. I'm going, wait a minute, dude. I don't see 5x to the 4th minus 1. But these two. I see a power 5 here. I see a power 4. We said 5x to the fourth was the derivative piece, minus 1. And so basically, I know right away I can cross out this guy right here. No, because that's a power 5. And so what I'm looking over here is this has got a power 4. That's got a piece that I want. But I'm not seeing 5x to the fourth minus 1. But it's in disguise. Hey, notice what would happen if we took out a 3 from these two terms here. If we took a 3 out of this 15, that'll leave us a 5. We take a 3 out of this 3, that'll leave us 1. And so what we really have here is a quantity that's really 3 times 5x to the fourth minus 1. So sometimes the derivative of the inside is in disguise. And so that would be the one that's the result of a chain rule. And then I give you 3 more to see what the result of the chain rule is. And basically 2 of them are and 1 is not. And the key point that I'm looking at here is the inside piece for an exponential. The inside piece is what's inside the power there, the exponent. And the derivative of 4x is 4. So I don't need an x here. I don't have an x on this one. That's good because when I do the derivative of 4x, I just get a nice number. And in 32, I got a 4. So this one would be the result of a chain rule. But over here to the right, I've got a 4x squared. When I do its derivative, I get 8x. And I'm noticing, dude, there's no x here. It's a 32. I know 8 goes into 32, but there's no x. And so what I've got here is a case where that top right one is not the result of the chain rule. It's the bottom one because I have the x there. So these two right here are actually results of chain rules. Now, because they're results of chain rules, we can actually do the two-step process to go backwards and find the antiderivative, whose function was the result that gave us these derivatives. And that's what we play. And so here's what we got, some examples of the antiderivative doing the two-step process that I talked about. And so what I'm looking at here is I got 2x over x squared minus or plus 1. I'm calling the inside piece will be downstairs. Downstairs in the denominator is my inside piece. And so the derivative of that would be 2x. So the first step was to divide the derivative of the inside, which is the 2x. So when I divide that out, the 2x goes away. I got a 1. So I'm looking now as this is my main piece here. 1 over x squared plus 1. 1 over something. And so you may recall 1 over, when we have 1 over something, the antiderivative of that was ln, the natural log. So what I'm looking at here is the antiderivative of the fraction 1 over something is going to be ln. And so what I have here is ln of x squared plus 1. And so that's basically the two-step process. I divided out the derivative of the inside, and then I did the derivative of the outside, and that's what I have. Again, this is not the formal U substitution. We'll talk about that in the next episode. But this is just kind of getting the idea of the antiderivative and what it's doing. Okay, so the antiderivative of 32e to the 4x. Well, the inside piece is 4x. The derivative of the inside is 4, so I divide that out. I get 8. And then the derivative of the outside, that's the exponential, is itself. And so basically the antiderivative of the e piece is going to be 8e to the 4x. And there is our antiderivative of 32e to the 4x. Okay, just a nice little two-step doing the opposite things in the opposite order. And on this next one here, I've got 4x squared is the inside piece. And so its derivative is going to be 8x. So I divide 8x. 32x divided by 8x is going to give me a 4. And then I take the antiderivative of that piece, and that would give a derivative of the e is antiderivative of e is itself. And so this is our original function. If we take the derivative of 4e to the 4x squared, if we take the derivative of this guy, we would actually end up with 32x e to the 4x squared. So it actually will come back in the wash if we do it. And our last example of the antiderivative is this really complicated looking one. But remember, we're calling the inside the part of the root, the seventh root here is our inside piece. Its derivative is 5x to the fourth minus 1. We're going to divide that out. That's going to leave us 3 here because remember, this is just 3 times as big as that 5x to the fourth minus 1. Multiply that by 3, and that's where we're getting this piece. So that's where that 3 comes from, because what we have started was 3 times as much as what we had for the derivative of the inside. And then our next step is to do the antiderivative of the outside piece. The outside piece is the 7th root, and you may remember that we add 1 to the power, so that'd be an 8 over 7. That'll be our new power, and then we divide by that new power. And so dividing by 8/7 is the same thing as multiplying by 7/8. Remember, when you divide by a fraction, you can take the reciprocal and multiply. So I've got that 3 times the 7 when we flip that. That's where the 21 comes from. The 8's going to be downstairs now. And then basically we have the stuff that's inside. That x to the 5th minus x is now to the 8/7 power. And so that would be the 7th root and all that stuff to the 8th power. And so that's basically doing the reverse chain rule using the opposite order, opposite thing, using the pure inverse relationship. Okay, so that's my beginning thing. Next episode, what we'll be looking at is how do we use U substitution to do these problems.